Okay, so we continue on our work on extending what we know about the computation of stresses in beams. And that we are addressing right now the question, the issue of where the cross-section is made of more than one material. By the way, a very practical application of when the case of a section that is composed of more than one material is the case of overpasses in bridges. In that particular case, and we will do an example today, one finds, for example, let's say something like this, right? And something like this. And so, if you focus on, let's say, this part right here, you can see that you have some concrete, because this is concrete, right? This is the road slab where the cars are traveling by, right? Cars over here. So this is concrete, and then you have a steel beam. And that steel beam is normally connected to the concrete. And perhaps I mentioned this in the class, I don't know. But, and usually there are something called studs here that connect the two. And so we have concrete here and steel here. This is just one application. There are, of course, other applications in which you may find a cross-section in which the behavior is governed by more than one material. Okay? So, you will remember, so our task is to connect, loads I gotta write clear, loads to stresses. Okay, that's what we seek to do, to collect loads to stresses. Now, you know from your previous class in statics that for bending, you looked at something like a formula like this. Sigma is equal to my over I. Okay? Now I could present this material to you very formulaic and say the formula is this or that. I'm not going to opt for that. That's not how I visualize what the process of learning is. The process is to understand what one is doing. So let's go through the logic. Okay? Let's go through the logic and see what is the thing that we are going to do. We will have loads, and from those loads we're going to find moments, which are actually stress resultants. And the tool that we're going to use is statics, right? Because that's all we know right now. All our structures are statically determinate. So from loads we will get moments. Now, from moments, we will get, that is, at a given point, we will get curvatures. Or from moment, we will get curvature. Well, it depends how I want to work in plural or singular. Let me just work in singular. From load, we get moment. From moment, we get curvature. Okay, now, in this particular case, if we use the book notation for curvature, which is the Greek letter kappa, then we can say that in general, the curvature is given by the ratio of the moment divided by the flexural stiffness of the cross-section. And I'm going to write it like this: flexural stiffness. Okay? So, therefore, it's obvious that we have to know how to calculate the flexural stiffness to get the curvature. And so, I need to tell you how to compute flexural stiffness of a cross-section. Now, when you only have one material, then we would normally take that flexural stiffness is equal to EI. Okay? That's the flexural stiffness of a cross-section, the product of E times I. But for that, you need to have one E and one I, right? what we need to do is to understand that concept of flexural stiffness in a bit more generic manner than just a case of E and I. So we can still call it, if you'd like, in order to use the same idea and not to write flexural stiffness, we can write EI, but let's call it EF for EI effective, or in effect, this plays the role of EI. It's the flexural stiffness, okay? Now, once we have the curvature, I'm erasing here so I can continue on this logic. Once we have the curvature, we are going to go from curvature to strain, okay? And to go from curvature to strain is purely geometry. That is, we will simply use the assumption that plane sections remain plane. So it will be something like this. We will find that if this is the curvature, then, and this is the location of the neutral axis, this is the strain. And since the curvature is a very small angle, then we don't need to distinguish between tangle and tangent, so we simply have that strain is curvature times distance. So if that distance there is E, then we would say that the strain there is simply the curvature times E, right? So from curvature we go to strain, and then from strain we go to stress. And the relationship between stress and strain, or strain and stress, is what we've learned in the previous course in statics. In a generical sense, it can be more complex, and in fact we will address later on in this class a more complex version for more complex state of stresses. But in the simple uniaxial case that we're interested here, then stress is just simply the modulus of elasticity times the strain. Now, in this case, there may be more than one material. So which modulus of elasticity applies is the one at the point where you're calculating the stress. Just like, I guess we can call it sigma at I is equal to E at I times the strain at I, right? And the E and the strains could vary. So this is what we are going to be doing, is to illustrate how to apply this theory. That will be our task today, and to do an example. Now, let me let me just go over it one more time without having to write anything. And let me use over here an example, not an example, but an illustration to fix the mind. So let's say we have a beam here with some loads, right? So we have a beam with some loads. Our objective eventually is to know whether this beam can safely carry the loads, if we are an engineer designing the beam, or if we are an engineer checking, or if we are asked to see how much load the beam can take, or whatever it is that we are interested in. But we need to convert these loads into the stresses in the material due to the bending. Now this beam due to these loads will deform, right? And we'll learn it on, we'll calculate also how to deform it. But the point is that due to that load, there will be a shear diagram on this beam, and due to that load, there will be a moment diagram on that beam. Okay? So there will be a shear diagram and there will be a moment diagram. And let me exaggerate to make it clear. You can see I'm not trying to be anything in particular. At some point there is a moment which is maximum, right? So this is the maximum moment. Therefore the maximum stresses on my beam will take place at that cross section where the moment is maximum, right? And my task is to focus in this point to see how this moment produces stresses inside that cross section, bending stresses, normal stresses. So as I said, the goal is to go from loads to stresses, but we are not using sigma my over I. okay, which applies to the simple case of one material only, we are going to reason it as follows. From the loads and using statics, we will calculate the moment. From the moment, okay, or knowing the moment, we will compute at the section of that moment how much is the curvature, okay, by dividing the moment by the flexural stiffness. You don't know right now how to calculate the flexural stiffness for something that has more than one material, but I am about to tell you how that is done. Once that we know how to calculate the flexural stiffness, this is the simple matter of dividing the moment by the flexural stiffness to give us the curvature. Once we know the curvature is the slope of the strain diagram in the cross section, and it crosses zero at the neutral axis, which we will also have to locate. Once we know the strain, we know that's the angle, once we know the curvature, from the curvature we calculate the strain, wherever we are asked to calculate the stresses. So I will calculate the strains by simply multiplying the curvature times the distance. So you can see that strain is going to be curvature times distance to the point of interest where you want the stress. So kappa times E. And once we have the strain, then we want the stress, and for that we simply apply the relationship between stress and strain for uniaxial stress field, which is simply multiplying by the modulus of elasticity at that point. Okay? Now, I have used here, I have used here in this discussion the term curvature. It may be that to many of you this term is very clear, but it may be that to others it might not be so clear. So let me dedicate 1 minute or two, or a few minutes, to discuss, to make sure that when we talk about something, we know what we're talking about. I could just give you a definition and say curvature is this, but that's not satisfactory in my opinion. So let's first look at just this, right? Make sure we are clear. If I look at that line, just let's see that we know that what we are talking about. When we mention the word curvature, what we're talking about, because curvature is not a concept of structural analysis or structural engineering. It's a very generic idea that applies in all kinds of things, and I guess it's a geometric concept in the case that we're looking at here in the 2D situation. So if I have that line, which I just made up, right, and I want to know what is the curvature here at that point, what is it that I mean? What do I really want to know? Well, I think from a intuition point of view, the easiest way to visualize it is that if I want to draw that curve locally using a compass, I will need a certain opening for the compass so that the curve will follow the line there locally, right? Very, very, very small. So this is, and there will be a certain distance, which is the opening of the compass. Then by definition, the curvature at that point is 1 divided by the opening of the compass, or the radius of curvature. That is, so you can see that curvature has units of 1 over distance, okay? So inches to the -1, for example. Now, if I look at the curve, let me just change the curve slightly here. Let's say the curve was like this. Okay? If you look at this point right here in this curve, I can see that the radius of curvature there is small, right? That is, the thing is very curved. So rho is small, so here This is a point of high curvature, right? Because the compass opening is small. As opposed to here, which I cannot even tell which way it's curved. Or, over here where the radius of curvature might be, for, over there, very, very large. Okay? So this is a point of low curvature. Now, another way to see it, well, that's from a geometric point of view. Another way to see it mathematically speaking, imagine that I take a point after and a point before the location that I'm interested in. And I find what is the tangent here and what is the tangent here. Now let's call the first point the 0 point and the second point the 1 point. So that means that this angle of the first tangent is theta 0, the angle of the second tangent is theta 1, right? Now, if I imagine that I have a coordinate, or I define a coordinate S that is running, I can start it anywhere I want. Let's say I start it right there, and that S just goes with the curve, right? Just goes with the curve. So the value of S over here is S0, so many feet from where I start, and the value over here is S1, so many feet from where I start. Then, if I take theta 1 minus theta 0, that's how much the angle or the tangent rotated, right, between these 2 points. And if I divide how much the tangent rotated between the 2 points by the distance between the 2 points, I just have the average rate at which the angle changes, right? Now, if I take the limit of that quantity as delta S goes to 0, where delta S is just simply S1 minus S0. That is, if I make the 2 points closer and closer and closer and closer, then by definition I get the curvature. So the curvature is simply how much the angle rotates divided by the distance that you use to calculate the change in the limit when that is very, very small, where that distance approaches 0. Now, in practice, well, not in practice, I'm sorry. Let's just say, to finalize this, the angle theta 1 is normally, well, no, I don't need to go to that complication. What I want to say is that our lines in structural engineering are usually very shallow, right? Because we don't allow things to deform very much. We like things to stay kind of where they were before they were loaded. So we exaggerate, so when we draw the deflection of a beam, it's really exaggerated, right? The beams are not really deflected like that. We can hardly see them. But if I want to know the curvature here, I would have to divide the change in the angle between 2 points, right? Theta 1 minus theta 0, divided by the distance S1 minus S0. In practice, we simplify that and we use x1 minus x0. In other words, we replace S1 minus S0 by x1 minus x0. That is, we do not divide the change in the angle by the length of the beam between the 2 points, but by the distance in the horizontal before the beam deformed. And with that simplification, it turns out that the curvature formula is just simply the second derivative of the deflection with respect to x, provided that this simplification is accepted. Okay? This is, of course, x, and this is y. All right? So curvature is second derivative y with respect to x, provided that we have simplified with not moving along the line, but moving in the element before the deformation. Okay, so that should give you hopefully a clean idea of what's curvature, and that we're looking for our task, which is to calculate stresses given given moments, right? Now, in the class last time, I hopefully emphasized the distinction between principal axis and arbitrary axis and so on. So I hope that I clarified that point. So without emphasizing that again, let me explain the topic by means of a representative example. So let's apply what I've been talking about in this example. Let's take a section that has two materials. It's made up of well, actually, I don't like that. I want to be a little bit more to scale. I want to be a little bit more to scale. Not precisely, but a little bit. So let's say this is going to be more like this. Okay. Now, instead of fooling this thing with a bunch of stuff, I'm just going to say each plate is 12 inches by half an inch. This is steel. So this is a 12 by a half, a 12 by a half, a 12 by a half, okay? And this is concrete. This is steel. And this concrete is 4 inches this way. And it's 4 feet wide, which is going to be 48 inches. Okay?